Distributed Control Systems Philosophy Overview, modernized with latest technology. Modern process facilities utilize advanced distributed control and safety systems, DCSS, to achieve fully integrated autonomous operations with real-time monitoring and minimal operator intervention. Centralized control rooms equipped with intelligent AI-assisted operator stations oversee all process units, remote assets, and turbo compressors. Remote platforms are linked via high-speed 5G LoRaWAN or fiber optic networks with local edge computing capabilities to maintain autonomous control during network disruptions. Remote wellhead control, including choke management and emergency stop functions, is fully accessible from the main control environment via secure, encrypted protocols. DCSS architecture, next generation DCSS integrates advanced DCS SIL-3 rated ESD and FGS systems using modular, cyber-secure, cloud-ready architecture. Platforms from leading vendors now offer native integration of OPC UA, MQTT, and time-sensitive networking, TSN, to support seamless real-time communication, AI analytics, and IT/OT convergence. The architecture is based on redundant, distributed edge controllers with embedded ML capabilities for predictive response and local fault-tolerant safeguarding. High-performance computing nodes handle time-critical decisions with zero latency switchover and autonomous anomaly detection. System software. System software runs on hardened Linux-based real-time OS or containerized environments like Docker on Kubernetes clusters. All systems are vendor agnostic, open architecture with support for Python, IEC 61131.3 compliant structured programming, and low-code, no-code configuration environments. Software updates and patches are managed through secure DevOps pipelines. The user interface leverages web-based HMIs built on HTML5 and WebSocket technologies, accessible from authorized devices on zero-trust networks. Real-time event stream processing ensures resiliency against data bursts or interface lag. Legacy system interfaces. Legacy interfacing is achieved through protocol bridging gateways that support hardwired fail-safe relays for critical trips and encrypted digital links for diagnostics and low-priority data. Legacy ESD levels and interlocks are integrated through smart relays and signal conditioners compliant with IEC 61508 and 62443 standards. System interfaces. All communications use gigabit-capable fiber optics or industrial TSN Ethernet with redundancy, PRP HSR. Interfaces support OPC UA, Ethernet IP, Modbus TCP IP, and MQT protocols. Integration with third-party skids and subsystems leverages edge data brokers and protocol converters, minimizing custom code. All interface links are dual redundant and monitored continuously for data integrity. Human-machine interface. Operator interaction is achieved through AI-augmented interfaces featuring contextualized information delivery, voice-assisted diagnostics, and touch tablet-enabled navigation. Workstations support Ultra HD multi-monitor setups and mobile dashboards for supervisors. Visualization software provides dynamic process modeling, real-time simulation overlays, and customizable alerts. Operator roles and permissions are managed through biometric access and federated identity services, OAuth 2/SAML. Hardwired panels and emergency controls remain for fail-safe manual intervention. Engineering workstation. Engineering workstations function as cloud-enabled development environments supporting real-time system diagnostics, drag-and-drop configuration, Git integrated version control, and digital twin-based testing. Secure engineering access is enabled via VPN, multi-factor authentication, and role-based privilege escalation. The workstation includes plugins for AI-assisted loop tuning, logic validation, and simulation modeling. System reliability and availability. Latest systems are designed for 99.999% availability using independent safety, SIS and process control, PCS, layers, high-speed redundant I/O processors, smart wireless sensors with self-healing mesh networks, predictive diagnostics powered by machine learning, distributed UPS systems with lithium-ion energy storage. System architecture ensures no single point of failure impacts overall safety or control. All components conform to CL230 with hot swappable modules. System redundancy. Full redundancy extends to control processors, edge gateways, I/O, network interfaces, and power supplies. Redundant modules operate in parallel with instant fault-tolerant failover. Intelligent watchdog mechanisms continuously validate module health. Cloud-based backup systems enable virtualized controller fallback when hardware failure occurs. System response. Real-time process control operates with scan cycles as low as 10 milliseconds using deterministic networks and time-aware schedulers. Prioritized data processing ensures mission-critical loops are handled with zero jitter. Smart controllers dynamically allocate CPU cycles based on process criticality. Diagnostics and auto testing. Embedded diagnostics utilize edge AI to detect anomalies, predict failures, and alert operators preemptively. Real-time health dashboards visualize equipment performance. Remote maintenance is conducted over secure cloud tunnels with support for augmented reality, AR, overlays during troubleshooting. All diagnostics are logged and auditable. Historical data management. Time series data is stored in scalable, cloud-based historians, e.g. OSIsoft InfluxDB, with support for OPC UA, PubSub, and ODBC JDBC access. Data lakes ingest structured and unstructured data for advanced analytics and digital twin simulations. Reports are generated through intuitive BI tools like Power BI or Grafana, accessible from web portals and mobile apps. Built-in cybersecurity ensures encrypted backups and role-based data views. Power supply. Critical systems are powered by dual redundant smart UPS with remote monitoring, lithium-ion batteries, and SCADA integrated power diagnostics. Energy recovery systems and solar-assisted power options support green operation targets. UPS autonomy exceeds 120 minutes with failover to diesel gensets or microgrid backup. Printers. Event and report printing is largely virtualized with PDF-A, archival, cloud storage integration, and print-on-demand services. Hard copy printing is retained only for compliance-critical outputs using ruggedized, networked laser printers. System cabinets. System and marshalling cabinets are prefabricated with smart environmental monitoring, temperature, humidity, intrusion. Modular 19-inch racks include intelligent PDUs, automatic cable labeling, and vibration dampening frames. IS and non-IS sections are clearly segregated with NFC tagging for fast diagnostics. Marshalling cabinets. Modern marshalling cabinets feature universal I/O cards reducing signal-specific terminations, quick connect terminals with color-coded LEDs for status, compact IS barriers with diagnostic LEDs, integrated asset tags for IoT device tracking, toolless component removal for streamlined maintenance. Testing and inspection. Testing includes digital FAT with remote customer participation via live streaming, automated site scripts validated against digital twin, continuous commissioning through predictive verification models, cloud-based punch list management and reporting tools. Functional spare capacity. Systems are provisioned with 50% spare capacity in control modules, I/O points, and physical space. Spare allocation accounts for future digital expansions, e.g. edge analytics, wireless I/O, AI integration. UPS and network bandwidth include predictive scaling buffers. Future readiness. All components support modular relocation to centralized control centers without service interruption using plug-and-play architecture, virtualized controller instances, and hot failover. Migration to centralized or hybrid cloud-based control is achieved via containerized control services, ensuring flexibility and business continuity. Distributed control systems, modernized architecture, and functional approach. Architecture. The modern distributed control system, DCS, is designed on an open, modular architecture built for high-speed, fault-tolerant, and cyber-secure operation. Industrial Ethernet with time-sensitive networking, TSN, enables deterministic communication across geographically distributed assets. Edge-based controllers manage localized process areas with embedded analytics and synchronize with central control servers over a secure backbone. All nodes are capable of dual redundant operation with automatic switchover and no single point of failure. Systems support horizontal and vertical integration, linking plant floor equipment with enterprise-level platforms via standardized industrial protocols like OPC UA and MQTT. Operator workstations are thin client or web-enabled HMIs deployed on resilient hardware or virtualized environments. These clients connect to redundant servers that host real-time databases, trending engines, alarm event systems, and AI-based diagnostics. Field signals are digitized once and securely routed to all relevant subsystems, reducing duplication and maximizing signal fidelity. Integration gateways connect DCS to smart packages, e.g. turbo generators, MCCs, VFDs, and third-party skids through secure, high-speed serial or Ethernet links. The DCS supports high-performance control applications such as multivariable predictive control, MPC, model-based diagnostics, and real-time optimization. Native support for digital twins and hybrid simulation allows system validation and operator training without interrupting live plant operations. Functional requirements. The primary goal of the DCS is to enable autonomous control, predictive supervision, and data-driven decision support. The system acquires, processes, and displays data across all assets with sub-second latency. High-speed control loops are executed at edge or central processors depending on loop criticality. The platform supports closed-loop control using self-tuning PID and MPC algorithms, real-time trending, analytics, and visualization at operator stations, remote monitoring and diagnostics via web-based dashboards, contextual notification of abnormal conditions based on rule engines or AI triggers, embedded logic control supporting Boolean, sequential, batch, and SFC programming models, live simulation environments for process testing, logic validation, and operator rehearsal, full online-offline reconfiguration with zero-impact deployment, integration with safety systems, SIS, FGS, MCCs, and intelligent instrumentation. Data integrity is maintained via distributed timestamping and synchronization protocols, e.g. I-1588 PTP. The system's historian supports long-term trend reconstruction and advanced analytics. Data communication. All communication channels use industrial-grade fiber optics, shielded Ethernet, or 5G-enabled edge gateways for high availability and low latency. Networks are fully redundant using ring or mesh topology with failover capabilities. Process data is streamed using OPC UA PubSub or MQTT-SN with encrypted payloads and certificate-based authentication. Each node maintains high-bandwidth links 1 gigabit sets with performance isolation for real-time traffic. Field and subsystem devices, e.g. turbocompressors, VFDs, Smart MCC, are integrated through secure industrial protocols, Profinet, Ethernet IP, Modbus TCP, and smart gateways. Subsystems provide diagnostic and configuration data directly to the DCS via secure APIs. Communication interfaces support prioritization, quality of service, QoS, and packet buffering to guarantee timely delivery of critical data. Upon link failure, controllers revert to last good state holding or safe fallback modes. Time series data is buffered locally for retransmission once connectivity resumes. Operator interface. Operator access is delivered through multimodal HMIs, available on wall-mounted panels, desk-mounted multi-monitor stations, mobile tablets, and AR/VR wearable interfaces. These interfaces offer real-time system status and contextual guidance, multi-layered process visualizations, e.g. PNID overlays, trend graphics, asset health indicators, role-based navigation and command execution, voice and gesture recognition for hands-free interaction, digital logbooks for shift handovers and operator notes, workflow engines to guide response procedures, alarm rationalization and suppression management tools, cybersecurity awareness prompts, and event logging. All operator interactions are logged with timestamp and user identification, forming a comprehensive audit trail. Dynamic screen loading adapts based on operator location, active unit status, and operational context. Events are time-tagged at the source using synchronized clocks and routed to the sequence events SOE recorder with sub-millisecond resolution. Faults, overrides, and operator interventions are displayed in real time and archived for future analysis. The interface extends to cloud or remote support environments where supervisors, maintenance engineers, or cybersecurity teams can securely review or interact with the system as permitted. Functional requirements, modernized. Modern distributed control systems are built to serve as the cognitive core of industrial operations, capable of fast, accurate process regulation, intelligent diagnostics, secure data handling, and autonomous optimization. The functional scope has evolved beyond traditional control to encompass dynamic system intelligence, predictive capabilities, and seamless IT-OT convergence. Key functional capabilities include advanced process control and self-tuning. Controllers support adaptive PID, model predictive control, MPC, and AI-augmented tuning. Control loops continuously optimize performance by adjusting gain, dead time, and process variable relationships in real time, ensuring stability even under process disturbances or equipment aging. Real-time data acquisition and contextual visualization. High-speed data acquisition enables sub-second capture of all critical parameters. Process data is contextually organized and presented to operators using layered displays, including interactive PNIDs, 3D equipment models, and trend overlays. Displays are dynamically filtered based on role, proximity, and current system state. Interoperable node communication. Distributed nodes, including controllers, servers, edge devices, and gateways, exchange information through standardized industrial protocols, e.g., OPC UA, DDS, MQTT. This allows seamless execution of control algorithms and system-wide state awareness. Time synchronization ensures coherent event tracking and coordinated control actions. Integrated diagnostics and predictive maintenance. The system performs real-time self-diagnostics across all components: control processors, I/O modules, sensors, actuators, and networks. Embedded analytics identify degradation trends, predict failures, and recommend preventive actions. Diagnostic dashboards visualize system health across all subsystems, contributing to reliability-centered maintenance. Comprehensive monitoring and event logging. Events, overrides, and equipment behaviors are logged with millisecond accuracy. Event correlation engines detect complex condition patterns and initiate preventive actions or operator guidance workflows. Intelligent filtering reduces cognitive load, surfacing only high-priority items. Native logic and sequence control. Logic and sequence control are executed locally in edge processors using structured programming, IEC 61131-3, function block diagrams, or graphical sequencers. Complex startup shutdown routines and batch operations are defined as modular templates for fast reuse and validation. User-centric application development. Engineers can build and deploy control logic, HMIs, alarm strategies, and data processing pipelines using visual drag-and-drop environments. Integrated development environments, IDEs, support version control, live simulation, automatic documentation, and cyber risk scanning. Remote engineering and virtual commissioning are enabled via secure cloud access. On-the-fly reconfiguration. Measurement ranges, logic parameters, control algorithms, and communication links can be modified online without interrupting operations. All changes are logged, validated through digital twins, and subject to multi-tier approval workflows. Plant intelligence and decision support. The system aggregates data into meaningful KPIs such as energy efficiency, throughput, and emissions, delivered through dashboards and AI-based advisors. Integration with enterprise platforms, ERP, CMMS, MES, enables bidirectional flow of production targets, maintenance alerts, and asset utilization metrics. Secure access and role-based control. Operators, engineers, and third-party vendors interact with the system through authenticated, encrypted channels. Access rights are enforced by granular, role-based policies and multi-factor authentication. Critical control functions are protected against unauthorized changes using tamper-evident logging and just-in-time access grants. Scalable historical database. A built-in time series historian stores high-resolution data for trends, machine learning, forensic analysis, and compliance reporting. The database supports edge local buffering with automated sync to cloud or on-prem data lakes. Users can export, query, or visualize data using open APIs and industry-standard tools. Overall, the functional architecture is designed not only to automate but to anticipate, recommend, and optimize, bridging the gap between operational control and intelligent industrial management.